much time, so let's start. So the first talk of this session is called ExpectAll, a BDD-based approach for link failure resilience in elastic optical networks, and it's going to be given by Jiri Srba from Aalborg University.
Okay, thank you very much for the introduction. And ExpectAll, yeah, that's the name of the tool and approach I'm going to present for failure resilience in elastic optical networks. Okay, now it's working. So the whole paper is motivated by a growing demand on higher bandwidth and shorter latency in computer networks. And in a fully optical networks, we eliminate one of the bottlenecks, and this is the conversion from optical to digital signal at every router. And that defines the so-called routing and spectrum assignment problem that I'm going to discuss today. And the idea is you need to find the light path and assign the frequency slots through the whole network. And in particular, in case of link failures, we need to quickly improvise and find an alternative path that avoids the failed links. And according to the technical specification, this should be done in less than 50 milliseconds. And in the worst case, 200 milliseconds. And then what we suggest is an approach based on binary decision diagrams that will find not only one solution, but in fact all solutions, including the optimal ones to this problem. And I will show you how we do it. So the routing and spectrum allocation problem is that we assume we have a number of traffic demands that transmit the data across the light path. And for every light path, we need to find a route and allocate the frequency slot that satisfies three conditions. So first, it has to be continuous. So we have to use the same frequency slots along the whole path. It has to be non-overlapping, which means that if I have two different light paths and they share the same link, they cannot share any of the frequency slots. And finally, it has to be contiguous, which means that if you need 10 slots, for the size of the demand, they have to follow each other. You cannot make gaps in between. So here is an example how a possible allocation can look like. And then we need to implement the fast failover. So links can and will fail due to different reasons. And we would like to quickly reconfigure the system. And the important things is that, first of all, correctness. So we have to reconfigure it to satisfy all the three conditions. It has to be fast, less than 50 milliseconds. We would also like to do it in a resource efficient or optimal way, because some of the configurations are better for future arriving demands than others. And possibly we would also let the operator to choose. So offer a number of solutions. For example, they might want to minimize the number of light paths that need to be reconfigured in case of a link failure. And the classical solution to this is over-allocate the spectrum. So for every... Let me try it here. I think it broke. Okay, does it still work? Yeah, good. So we can over-allocate. So that means for every primary path, we allocate also the spectrum for the secondary path. We can be a little bit smart that some of these can be shared. And this is very fast because we already allocated the spectrum. We are resilient to one link failures, but we waste lots of resources because they could be used for some other light path. And we would like to find some optimal resilience, not only for one link failure, but for arbitrary number of failing links. So a classical solution that was already presented in the literature is to use integer linear programming to solve the RSA problem. So I'm not going to details, but we implemented some of these classical solutions that we found in the literature to see how fast they can actually be. And then we evaluated on some small, medium-sized network topology, Deutsche Telekom and Kanto. And we generated some demands based on a gravity model and a real population size, and measured how much time does it take to compute a new solution or optimal solution. And as you can see, with the increasing number of link failures on the x-axis and the time needed on the y-axis, we need seconds. So this is definitely not going to allow us 50 millisecond reconfiguration time, in particular if we go to larger networks and more demands. So attempt number one would be, well, let's pre-compute it. So let's prepare for all the failure scenarios, but as you might expect, this is exploding in the number of links you will prepare yourself for. So we tried for a number of demands. If it's for one failure, you can prepare yourself in 3 minutes and then you can react immediately because you already know which path to use. For 2 link failures, 3 link failures, this starts taking hours, and with 4 and 5, this takes days and weeks to compute. So again, that solution does not scale. So the challenge is we would like to be resilient to arbitrary number of link failures, find optimal resource allocation, and be fast. So let me a little bit formally define the problem now. So in the RSA problem, we are given a number of demands. Each of them have a size. Let's say in my example, the size is just 1. For every demand, I have defined some path that I'm allowed to choose from when I want to shoot the light through the network. And depending actually how long is the path, you have to use different modulations, and some of them will require more frequency slots than others. So in my example, the path pi1 and pi3 has 3 hops, and that requires modulation that needs 2 frequency slots, whereas the short path, they only need 1. And then we have a number of frequency slots. Usually that's more than 300, but in my example, it's just 1 and 2. And then we can define the channels. These are all the contiguous slots that we can use. So they are just 3 possible channels I can use. And now I would like to say what is a solution. And solution is an assignment from every demand to the path that I choose, and also to some of the channels that are here. So for example, the solution that is highlighted over there is I choose the pi0 and pi2 for the demand 1 and 2. And let's say both of the demands, they use the channel 1. It's a short path, so according to the modulation, this is fine. And this is actually an optimal solution. And optimal in the sense that it minimizes the highest used frequency slot, because we would like to keep everything packed together in the beginning, so we are ready for the demands that come in the future. Is another solution. I can keep the path pi0, but the second demand will take the path, the 3-hop path. In this case, I have to use a different channel. Because it's a longer path, so I will use 2 slots, 1 and 2. And that's again a correct solution, however, not optimal anymore because the highest frequency slot is now 2. So now the failover problem is that I assume I have some set of failing edges, E-fail, or size at most k, and I want to find a solution, the path and spectrum assignment that avoids such that every path intersection with the failing edges is an empty set. So that's pretty simple problem. And now when links fail, for example, if V2 and V6 link is not available anymore, we don't have this as a solution as you would expect, and suddenly this is now an optimal solution because you cannot find a better one. And the task is to find this fast. So in ExpectAll, we compactly encode not just one, but all solutions to the RSA problem. And then we can quickly find a solution because it's already pre-computed. We use binary decision diagrams for that purpose. So binary decision diagrams is a data structure that allows compactly represent Boolean functions. It's a rooted acyclic graph. There are two terminal leaf nodes, true and false. Usually the false is not shown and all the edges that go there are omitted, like in my example. And every node has a label of a Boolean variable, and typically two outgoing edges, the high and low edge. High means we set the variable to true, low means we set it to false. And then when you have a pass from the root to the terminal node 1, this actually gives you a satisfying assignment or the, that is represented by the BDD. Sorry. I think it's better now. I made a note. Good. So how do we do the encoding? We need to define the Boolean variables, and so for every channel, we will have, for every demand, we will have the encoding of channels, and we only need log 2 of the number of channels Boolean variables for that. And for every pass that is in the D pass of the demand, we also need some variables to encode that. And the whole solution is encoded that, you know, for every demand we have the path encoding and the channel encoding. So first we can define a BDD which is defining the assignment. So I say that for every demand D, I have a disjunction over all paths that is available to take, and then I have encoding that, you know, that path is encoding in the variables of that demand. And there is some fixed encoding scheme that I assume is sort of defined implicitly. And then I say that now there is an OR, and then for all channels that can be on that demand and that have the proper size, that means the modulation times the size of the demand, they have to encode, they have to be encoded in the BDD. So as an example, in my running example, when I do the assignment BDD, it looks like this. And here is the encoding that I used. So first the path. Here I only need 1 bit for encoding the path. Each of them has just 2 options. So this is 1, 1, which corresponds to pi 1, pi 3. And then I have 2 bits that encode the channel of the first demand, which in my case is 0, 0, 1. And 0, 1, this is the channel 1, 2. And then the other one is also 0, 1. That's also channel 1, 2. So that path encodes this concrete assignment. As you can see, I'm already breaking the non-overlapping condition here, so I need to intersect this BDD with the one that actually guarantees that these properties hold. And it's the no-clash BDD, which looks like this. And it says that for all demands and all paths in those demands that actually intersect, either these 2 demands are not scheduled to take these paths, or if they are, then for any channels that actually have some common slots, they cannot be encoded in both demands. So that's how it works. And when I build this no-clash BDD, it looks like this, and it encodes all the bad assignments that are clashing. Well, it accounts all the good ones. There is actually only one that is clashing. And you see there is this one long path that actually goes to the node 0 that I omitted. And that's the assignment which takes pi 1 and pi 3, and then 0, 1, 0, 1, which is this 1, 2. And that's the clashing assignment that is now excluded in the BDD. And then what do? We simply take intersection of these BDDs because they are closed under the operation, and we get the RSA all BDD, which encodes all the correct assignments. So this is an example of that intersection of these two, and this is what it looks like. And when I keep it here and I go to my example, I can, for example, see how the solution 1 is encoded. So solution 1 should be the path pi 0, which is 0. That's this. The other is pi 2, which is 0. So we are getting here. Here you can see that the first bit of the first channel is skipped, so actually it can be 0 or 1, and the second one has to be 0. So in fact, this encodes that either the channel assignment can be 1 or 2. And the same, the first bit of the second is skipped, so the second bit also says it has to be 0, so it can be the channel 1 or 2. So this path actually encodes 4 different solutions, including the one that I depicted in my running example. Okay, so now we can build the BDD. All the solutions are there. We would like to extract the optimal ones, those that actually minimize the highest used slot. And it's done by a small trick. So we introduce some new Boolean variables, depending what is the maximum number of slots we have. And to the RSA, we conjunct that for every demand over all channels, if we encode that channel on that demand, then we have to set all the variables SF that are smaller than the maximum slot in that channel. We have to set them to true. And now the question is simply, what is the smallest BDD like that has a solution and some of the SF is false? Let's find the smallest slot that we can set this variable to false and it still has a solution. And we can do some binary search and relatively quickly find the optimal solution in this way. Okay, so now we could be already done. We know how to construct the BDD. We know how to get all the optimal solutions, but we would like to speed it up. So sometimes there are some redundant solutions that we are actually not interested in. And this may result in a huge construction time of those BDDs. And we suggest 3 techniques how we can reduce it. So first, we can actually compute the sum over all demands, what is the maximum number of slots they need, and we simply limit the number of slots to this maximum value. Because we know if there is a solution, there will be also a solution that doesn't use more than that many slots. So instead of exploring this huge state space, we just limit it to 9 in this case, and we know the solution will be there. So that's pretty simple technique. We introduced another that is called gap-free restriction. And the idea is that in the optimal solution, we assume that every demand must either start in the lowest slot 1, or if it's not possible, it has to directly follow after another demand that overlaps with it at least on one edge. So for example, this is not a gap-free solution, but this is the only demands that actually overlap is D2 and D3, but all the others, they have to start on slot 1, and then I have to order these in one way or another. So again, that's a safe restriction. It preserves all the optimal solutions and allows us to speed it up. There is a way how you encode it into BDD. We also have yet another restrictions that remove symmetries, because we don't really care whether the demands are ordered like this or like that. These are symmetric solutions, so we simply impose some ordering on the demands and say that first we start from D1 and then D2, and there is a formula that guarantees that the ordering is kept. This is not completely safe. We can actually arrive to an empty BDD even if there is a solution. But on the whole benchmark, when we tried, this was never the case. And if there is a solution, the optimal solution is present there as well. Good. So now we know how to construct the BDDs with all solutions. We know how to speed it up. So how do we apply it to our failover protection? So the first obvious method is called a deletion. So suddenly somebody gives me the set of failing edges. So what I do, I just take my precomputed BDD and I intersect it with sort of postulating that none of the demands can use the path that actually contain the failing edge. It's a relatively fast operation, and then I get the prune BDD with all the solutions that avoid the failing edge or failing edges. The slight problem is it's not completely fast. It can, in some cases, exceed this 50 milliseconds, but it's definitely orders of magnitude faster than the ILP. I will show you some plots soon. So we came up with a different solution. So why don't we encode the failing links already into the BDD? So it's actually pre-computed. So in case of one failing link, in my example, I have 7 edges, so I need 3 Boolean variables to encode the failing links. And in the beginning of my BDD, I actually encode what are the options of how they can fail. And if, for example, this is failing, this is 0, 0, 1, 0, 0, 1, this is H1 is failing, then I have the BDD of all the solutions with assuming that that H is failing. And of course, you can do it for more than one, but then it starts exploding because you need to introduce more and more variables. So we implemented ExpectAll in a Python using the CUDD wrapper. So the wrapper for the CUDD binary for BDD. We evaluate it on the Deutsche Telekom and Canto topologies. We do 1,000 random link failures up to 5 failing links and see how these methods perform. So here are the plots. If I take a look, for example, at the Canto topology, you can see the ILP fast failover solution. This takes a few seconds. The deletion is initially very fast, but it scales not too good with the increasing number of the demands. The precomputation, on the other hand, is almost constant. So this is a box plot, so you can see the averages. This is 50 milliseconds line, this is 200 milliseconds line. So we are for sure pretty good satisfying the requirement. In Deutsche Telekom, the picture looks very, very similar. What is interesting on the other hand is the build time. So of course we have to invest in building those BDDs. So what is the build time? So I already showed you if you use the ILP and you would pre-compute everything, this will grow exponentially with the number of failing links as you would expect. This is logarithmic build time on the y-axis. So in both, this is definitely going to explode. The deletion is very nice because you compute it once, and irrelevant how many failed links you have, it doesn't change. It's a constant. There's a small deviation because of the measurements in the experiment. And the precomputation is also pretty good. It has a slight, increase with more failing links, but it's not too bad. Of course, what is a little bit bad is that how does it scale with the number of demands? So this is for 7, 8, and 9 demands, and you see we always make a jump that is exponential. So as it is right now, up to 9 demands, we can pre-compute it, let's say, in 1 hour, which is acceptable time because then we are ready within 50 milliseconds to react to any failing links. But of course, the number 9 is a little bit limiting. So in conclusion, we introduced ExpectAll. This is a tool that computes BDD representation of all, including the optimal solutions to the route and spectrum assignment problem. It outperforms the existing ILP approaches both in the query time and build time, but it still suffers from the scalability and it's not yet applicable for more than 9 demands. So how we can remedy this? Well, we should think more, see whether we can find more restrictions. We still have way too many redundant solutions. So if we manage to find some clever lemmas that say you don't have to do this and that, we can further improve the performance. But what about application in practice? So 9 demands is usually not enough. So what do you do? Well, you can select some very critical demands you want to protect in an optimal way. They should typically be long-lasting and large volume. And what do you do? In the beginning of the spectrum, you simply use this optimal method using BDD. You can pre-compute the solutions. You are guaranteed to have optimal protection there. And for the other demands that are less important, less critical and smaller, we just use some of the existing heuristic approaches, for example, that are not known to be optimal, but we just start to do them from the other side of the spectrum. So that could be one way how to, remedy this, but we would definitely like to work more on improving the performance. Yeah, and that was my 25 minutes, so thank you for your attention.
Thanks for the wonderful talk and being so precisely on time. Yeah.
Oh, I need the mic. So it's really nice. I enjoyed it. So one question I had is, if you already have an ILP, why don't you just take each constraint, make a BDD, and intersect all of them? And you don't need to work so hard to construct a BDD, right? Every constraint is some Boolean values. You could construct a BDD and then just intersect all of them.
I think it's an interesting idea. I think the problem a little bit is, even though these building blocks are small, once we start intersecting them, we can, the BDDs will start growing. And because it's unique, at the end we arrive to the same size of the BDD as we would using the other method.
Right.
So, but yeah.
The other question is, did you have to drop any of the original problem constraints that couldn't fit inside this kind of a BDD? Or, the ILP basically captures everything. The question is, does the ILP capture everything, or are there things that are soft constraints, you don't capture them somehow?
The ILP finds one solution. So in the literature, you have all these constraints that it's good, and then you have to set your function you want to minimize, and that can be many different things, but most commonly in the literature, people would like to minimize the maximum slot. So you run the ILP and you get just one solution, and that solution for sure is inside of our BDD. But we offer more. There could be more optimal solutions or suboptimal that the operator might prefer for some other reason. So they can say, I don't want this path to go through Iceland, for example, because the connection is unstable or whatever. So you can put additional restrictions as a conjunction to the BDD and sort of navigate through the space, which that's, I think, is the advantage of the BDDs. Yeah.
So, Kedar.
Yeah, thanks. This was really interesting. So I work at Bell Labs, which is part of Nokia. So I don't do this, but I have colleagues who do stuff like this. So I was curious if there are other ways of defining optimality, because one of the constraints I've heard is that you don't want to switch too many paths. That's the optimality criterion. So if a link breaks, then you do have to make some changes, but you don't want to make too many changes because setting up these light paths takes some amount of time. So I don't know if that's correct. This is just something I vaguely remember hearing.
This is excellent question, because I think this is primarily what the operators would like to do. Keep all the paths running and only do the necessary minimum to reshuffle. And indeed, we do it, and we have a section in the paper where we describe how you can optimize it for that criterion and how to construct the BDD. I dropped it because of the lack of time, but indeed, that's something that is possible, and you can read it in the paper.
Then I can use my chairly privileges to ask a few questions. One thing I was very curious about is, how much does the size of your BDD and the computation time depend on things like variable order? Did you have to do any tuning to optimize that? That's one question, and then I have a follow-up.
Yeah. So this is again another excellent question. Of course, the variable ordering is extremely important, and we have tried some smaller models. And we exhaustively tried all the permutations of the variables. Not like, there are too many, but there are these blocks like the pass, cost variables. Is it better to have pass first or cost, or interleave them? And actually this was done by master thesis students. So they spent lots of time, try all the permutation until they found the one that actually works good in this case. And this is first the path, then the cost variables. So if you do it slightly differently, you can get exponentially larger BDDs very, very quickly. Yeah.
And then one thing I noticed is all the integer constraints were kind of bit blasted in a way to make it into the BDD, right? I mean, did you consider using like multi-value BDDs or multi-value decision diagrams to represent the integer?
No, we did not get that far. I think it could be maybe a way how to improve that. I think usually these numbers are not too big. So on a typical network, you have like 320 slots, and then the modulations numbers are depending what kind of modules, between 2 to 12 maybe. So these are not big numbers to encode. You can do with a small number of bits. So that's why we did not consider that. I don't know if it would speed it up or not. It's something to try. You never know with BDDs or how things behave until you try. So.
Okay, I think that's concludes the time for questions. Please ask more questions offline. And I would like the next speaker to set up this.
Thank you.